Episode 20 of the World of FPGA podcast. Let us talk about simulations and their benefits for your FPGA development projects. Welcome to the World of FPGA podcast. I'm your host, David Kirchner, and I will lead you through the world of FPGA. And now, let's begin. Welcome to this episode about simulations. So what are simulations in general? Simulations in general refer to the process of creating a model or representation of a real-world system in order to understand its behavior and make predictions. So far, so good. So simulations can be used in various fields, including science, engineering, and computer programming, to test hypotheses, analyze complex systems, and simulate scenarios that may be difficult or costly to replicate in reality. That's just a general description of simulations, but what are simulations in FPGA development? In the context of FPGA development, simulations plays a crucial role. They involve creating virtual models of the FPGA design and run them in a simulated environment, just to verify their functionality before deploying them on a physical FPGA board. This allows developers just to catch and rectify potential errors and bugs in the design early on, saving time and, what is also impossible, saving resources. And the benefit, and that's the main part of this podcast episode, the benefits for your FPGA projects. Well, there are numerous advantages and benefits that come with incorporating simulations into your FPGA development projects. Firstly, simulations offers a secure and a controlled environment in which you can test and validate your design without the worry of potential damage of physical hardware. This means that you can experiment freely and just make necessary adjustments without the fear of negative consequences. That's always a good idea to simulate before you destroy your $50,000 FPGA development board. Secondly, simulations just provide you with the opportunity to explore various design possibilities and also optimize the performance. While by running just multiple simulations with just some different parameters, you can fine-tune your FPGA design and also achieve the best possible results if it's possible to modify these different parameters. This flexibility allows you to experiment with different configurations and find the most efficient solution, if possible, for your specific requirement. In addition to these benefits, simulation also play a crucial role in debugging and also in, of course, troubleshooting. They offer detailed insight into the inner working of your FPGA design, allowing you identifying and address any potential issue or errors. This level of visibility is invaluable in ensuring the reliability and functionality of your final product. Overall, incorporating simulations into your FPGA development process offers a multitude of advantages. While from providing a safe test environment to enable design optimization and facilitating in-depth debugging, simulations are an essential tool for successful FPGA development. While furthermore, simulations offers the advantage of time and also cost saving. By using simulations to test and validate your FPGA design, you can significantly reduce the time and resource requirements for physical prototyping and also testing. This means that you can iterate and refine your design more quickly, accelerating the overall development process and bring your product to market faster. Additionally, simulations allows for easier collaboration and knowledge sharing among teams members. With simulations, multiple engineers can work on different aspects of the FPGA design just simultaneously without the need for physical hardware. This promotes efficient teamwork and allows for the exchange of ideas and expertise in a virtual environment. But how to start with simulations? When embarking on the journey of simulations in FPGA development, it is crucial to begin with the necessary preparations. The preparations usually entailed employing specialized software tools such as an HDL simulator, so a hardware description language simulators, or a software development kit that are provided by the FPGA vendors. To begin, you will need to either write or import the FPGA design code into your simulation environment. This step is pivotal in ensuring that your design is accurately represented and can be subjected to thorough testing. Additionally, it is important to establish the appropriate test benches or stimuli, what will serve as simulated inputs for your design. These test benches or stimuli are essential for emulating real-world scenarios and evaluating the functionality of your design. Finally, it is crucial to define the desired outputs that you wish to observe and analyze during the simulation. This will allow you to gain valuable insights into the behavior and performance of your FPGA design, enabling you to identify any potential issues or areas for improvement. By following these steps and embracing the power of simulations, you can enhance your FPGA development process and pave the way for successful implementation. But what are the boundaries of simulations? The boundaries of simulations refer to the limits or constraints within which a simulation can operate. These boundaries define the scope and parameters of the simulation, determining what can and cannot be simulated. Understanding the boundaries is crucial for the determine how accurately and realistically the simulation can replicate the real-world system that has been modeled. By defining these boundaries, simulation designers ensure that the simulation remains focused and relevant, enabling users to efficiently analyze, predict, and make informed decisions based on the simulated outcomes. Therefore, identifying and understanding the boundaries of simulation is essential for its successful applications in various fields such as science, engineering, and so on. It allows for the effective utilization of the powerful tool to explore and to understand the complex system, to predict future scenarios, and so on. Overall, the boundaries of simulation provide a framework within the simulations can be developed and utilized, enabling us to gain valuable insights and knowledge about the systems we seek to understand and improve. One important additional question is just, should we simulate the whole design or should we just simulate only modules? When considering the simulation of an FPGA during development, the decision to simulate the entire design or only specific modules is a tactical one that can have significant implications on the development cycle, resources allocations, and eventually success of the project. Each approach has its merits and potential drawbacks, which must be weighted carefully by the development team. On the one hand, we can simulate a whole design. Simulating the entire FPGA design is a comprehensive approach that allows developers to verify the interaction between all modules and the overall behavior of the system. This is particularly crucial in the later stages of development to ensure that the integrated components function together as intended. The advantages here are integrated testing. It validates the interfaces between different modules and ensure the way of communication between them if the communication is correctly. Another is the timing analysis. This enables the verification of timing constraints across the entire design to ensure that the FPGA will perform as expected in real-world scenarios. And there's the system-level performance. Assesses how modifications in one module might affect the performance of another, providing a holistic view of design efficiency. But there are also disadvantages to simulate a whole design. It is just resource intensive. Simulating complex designs can be extremely demanding in terms of computational resources and time. Another one is the difficulty in isolating bugs. When a problem is detected, it can be challenging to point out its source within a vast and interconnected system. If you're just simulating only modules, you're focusing simulation on individual modules or subsets of this design, can be also advantages, in particular in the early phase of development or when working on large-scale or complex FPGA designs. The advantages are at first efficiency. It is much faster to run and generally require fewer computational resources, allowing rapid iterations and more frequent testing. The isolation of bugs is easier. When a defect is found in a module simulation, it's usually easier to isolate and address because fewer variables are involved. Well, and we have the advantage of parallel development. Module simulations allow different teams or team members to work on separate parts of the design concurrently, potentially speeding up the development process. But there are also some disadvantages. We have a limited system view. Simulation modules in isolation doesn't provide insight into how they will operate when integrated with other parts of the design. And we are missing the interactions, potential problems that arise from interactions between modules may go undetected until full system simulation or actual hardware integration occurs. Well, in practice, a more hybrid approach is often adopted, where individual modules are simulated and verified before being integrated into larger blocks of the whole system for the further simulation. This staged approach allows you thorough testing at each level of complexity. Early on, when individual blocks are being designed and tested, module-level simulation is prevalent. As the design matures and modules are combined to form larger functional units, simulations often expand in scope to include these integrated blocks. Finally, once all or most parts of the FPGA design are stable and integrated, whole design simulation becomes critical to ensure that the system operates correctly as a whole, meeting all specifications and performance criteria. The decision on how to approach FPGA simulations also depends on factors such as project deadline, available tools, just hardware complexity, and specific project or industry standards. Thus, it's essential to balance these factors with simulation goals to optimize the development workflow, ensuring both efficiency and thoroughness in testing. In summary, simulations are a powerful tool in FPGA development, just offering numerous benefits such as error detecting, performance optimization, and debugging capabilities. By starting with simulations and carefully defining their boundaries, developers can ensure the reliability and functionality of their FPGA designs, well, just before deploying them on physical hardware. At the next episode, we will dive deeper into simulation with VHDL. Further information can be found at world-of-fpga.com/WFP020. If you found this episode helpful, please rate it on Apple Podcasts and share it with your colleagues and friends. That's the end of today's podcast episode. Thank you for listening and for your attention. So I say goodbye here next time, your David Kirchner.